So for problem number 61 in our textbook, let me read it to you guys out loud. It says, in a high-speed chase, a policeman's car bumps a criminal's car directly from behind to get his attention. The policeman's car is moving at 40 meters per second to the right and has a total mass of 1,800 kilograms. The criminal's car is initially moving in the same direction, but he has a velocity of 38 meters per second, and his car has a total mass of 1,500 kilograms. Assuming that it's an elastic collision, determine the two velocities immediately after the bump. All right, so what was the mass of this car? 1,800 kilograms, right? What was his velocity? You guys have your books open?
Yes.
40 meters per second. And it's in the positive direction. So let's just establish that. We're saying that going to the right is positive, right? And going to the left is negative. And I don't think anybody will go negative. I think everything's going to go positive. And so my criminal, who has a very fancy car, his car has a mass of 1,500 kilograms and a velocity of 38 meters per second to the right. So they're in a high-speed chase, right? And so the police car wants to get the criminal's attention. Boom. He hits the car. Now it says it's an elastic collision, right? So it's an elastic collision. What does that mean? Yeah, he's going to give him a little push. I would like to refer to it as a love tap. All right, so he gives him a little love tap. Now that's going to cause his car to go forward a little bit, and maybe the police cars, we don't know what they're going to do. We're going to calculate. Maybe the car will slow down a little bit. I don't think that the police car will speed up. Does that make sense? Because what happens is when the police car bumps him, a little bit of that police car's momentum or energy or however you want to think about it gets transferred to the criminal's car. Okay? So, how do we calculate this? Well, it's a conservation of momentum, and we could write out that great big long problem, or we could use those equations from page 212. Now, let me explain what I'm talking about. Okay, so normally, if we had more time, we do one of these things. It's a conservation of momentum, and we've got this initial final deal. And what that means is that the momentum of the police car, right, which is the mass of the police car times the velocity of the police car, plus the momentum of the criminal's car, which is the mass times the velocity, right? The initial conditions, those two there. If I add those up, they should be equal to this, all right? The final velocities, basically. And that's what we're being asked to do. So we have two unknowns, and this is just like, I think, problem number 57. And then if I algebraically go through this long rigmarole, I can solve for this, and I can solve for that. But we already have them solved for in the textbook. So if you look in your textbook tells us that the velocity, the final velocity of the police car is equal to the mass of the police car minus the mass of the criminal's car all over the mass of the police car plus the mass of the criminal's car. And basically what they did is they took this whole equation and algebraically solved for the velocity of the police car. Okay? So if we skipped all those steps and we came down to it, we get something like this times the initial velocity of the police car plus 2 times the mass of the criminal's car all over the mass of the police car plus the mass of the criminal's car times the velocity of the criminal's car, their initial. And basically what I'm doing, this equation here, they took this. Well, actually, they took this equation here and solved for VP, and that's how you get all this stuff, right? So we're gonna plug and chug, right? We're gonna plug that in, And I see, as I look out at you guys, I see some of you guys are already doing that, and that's good. So, the rest of you guys can tell me this stuff. So, the velocity of this thing is equal to, what's the mass of the police car?
18.
Minus the 1,500. That's the criminals. And so then on the bottom we have 1,800 plus 1,500 times the velocity of the police car, which is 40 meters per second, right? Make sure that it's kilograms and meters per second. I did, so we didn't have to do any conversions. Plus 2 times the mass of the police or the criminal's car, all over 1,800 plus 1,500 times the quantity. What was the initial velocity of the criminal's car? 38, right? Let me check my notes, make sure I didn't make any mistakes. Now, if you do all that work, what do you get? We get that the velocity, the final velocity of the police car should be about 38.2 meters per second. Because the kilograms and stuff will cancel out. Because you have kilograms on the top, kilograms here, kilograms on the top, kilograms here, so they cancel out. Does that make sense? Okay, so now are we done? No. We got to do the velocity of the criminal's car. And so you can find this in your textbook on page 212. And we get this thing, we see that this is 2 times the mass of the police car all over the mass of the police car plus the mass of the criminal's car times the initial velocity of the police car minus, not plus, minus the mass of the police car minus the mass of the criminal's car all over the mass of the police car plus the mass of the criminal's car times the velocity of the criminal's car, the initial one, right? So now, to get that equation, what they did is they came up here, and they took this equation and solved for the final velocity of the criminal's car. So algebraically, just to save time, I'm not going to do it. But if I solved that and moved all the other stuff all the way over to the other side, I would get this equation, okay? And I'd have to combine some things and arrange some things in a certain way, but that's the equation I would get, right? All right, so now let's plug it in. V sub c is equal to 2 times the mass of the police car, which is 1,800, right? And then the formula called for 1,800 plus 1,500 times the velocity of the police car, which is 40, the initial velocity minus 1,800 minus 1,500 kilograms, but the kilograms cancel, 1,800 plus 1,500 times the velocity of the criminal's car, which is 38. So they're basically kind of, well, they're almost identical equations, right? It's just they're a little different. So if you plug all that together in your calculator, did somebody do the math on your calculator? I wrote that down kind of quick, but I have my notes here. That should be 40.2 meters per second. Okay? Does that make sense? And do you guys see, I didn't derive it, but do you understand that if I took that conservation of momentum equation and solve for VC, I'll get something like this, right? We're just saving some time. The textbook gave it to us as a formula. We're just going to use the formula, okay? And you can make a flashcard of that for your test if you want, right? So now what does that mean? Well, that means if we come way up here, and I have a police car, right, and I have a criminal in a race car, and he starts off at 40 meters per second, and he gives this guy a little love tap. They're still both going to keep going, except now his final velocity will be, what was it? 38.2 meters per second. And now the criminal's car would be 40.2. Now is that real smart to bump into him? No, he's gonna get away. Alright. Does that make sense though to you guys?
Yeah.
Are we good?